Okay, so we've been talking about solving equations. We have lots to talk about on that account. So the first, to remind you generally of the strategy, the easiest case that there is the linear case. So it's an equation that looks like this: mx plus b is equal to c with a non-zero m. So the reason why it's called linear is because when you take this equation and you split it in the way that we've been doing, so y is mx plus b, we'll consider that, and the other side y is c. So when you plot y is c, that's going to be a horizontal line. And when you plot y is mx plus b, because m is not 0, this is going to be a line, but not a horizontal one. So it's either going to have positive slope or negative slope. So it's going to be some kind of line, like so. And then when you plot them on the same axis, so this red one could be y is mx plus b. And then the green one, something like this. So that's y is c. And then the question is do they intersect? The answer is yes. Right there at that point. And then the answer to our question is that point right there. And we already solved it. So if you were to solve that equation, either look in your notes or just quickly in your head, the answer is going to be c minus b over m. So that's that x right there. So that's the easiest possible case. So then last time we carefully considered a nonlinear case. The first nonlinear case is absolute value. Specifically, we considered absolute value x is equal to c. And just like we took the two sides of this equation and split it into two parts, we'll do that with this one and say, well, let's consider y is absolute x, and let's consider y is c. Again, y is c is a horizontal line, and you know, we took the time to plot this. What is the characteristic shape of absolute value? A V. So notably, there's a big distinction between a line and an absolute value, and that is, notice that the line goes all the way up, so you can't lift the green line above the red line because it goes all the way up, and the red line goes all the way down, so you can't pull the green line down far enough to where you get below the red line. You know, I only drew so much, but it goes infinitely far down. Whereas the absolute value, it does have a lowest point right there. So in principle, you can pull that green down and be below it. As a result, there are three possibilities. C could be negative, C could be 0, C could be positive. So all of these will have an absolute value. And then I'll make a line at height C. So if it has negative height, that means that the line is down here. If it's at height 0, then it's right on top of the x-axis. And if it's at positive height, like that. And just like we said last time, you know, we're interested in the number of intersections. Of course, here there's no intersections. Here there's exactly one intersection, and here there's exactly two. A typical example of this kind would be something like absolute x is -3. There's no solution. There's no input you can give to the absolute value, so that the output would be -3. Here, this could be something like absolute x is 0. The only possibility is that x is 0, the one and only possibility. And then here we could have something like absolute x is 3. And now in this case, in the picture, you can see, well, there has to be two possibilities. It has to be two. So this splits into x is -3 or x is 3, and then generally c or -c, and that one is 0. All right, so we did all that last time. I'm just bringing us back into the spirit of things. So a new one. If he keeps going, I'll say something. So we've got another one, nonlinear. Maybe I can just shut the door. Yeah, I'll try that. Did I not shut it? Is parabola. So that's the case we're on. So now we can say let y be x squared. So first we'll make a table of values. -3, -2, -1, 0, 1, 2, 3. And so what I'm asking is to fill in the table. So, you know, what for each x, what would it square to? Well, 9, 4, 1, 0, 1, 4, 9. Notice that those red numbers read the same forwards and backwards, and as a result, that sequence of numbers is said to be a palindrome. So the reason why I point that out is because when you plot those points, you'll see a symmetry. So I'll plot the ones that have no negatives in them first. So, and instead of making these be one unit, I'm going to make them two, so that these will all fit. So 0, 0, 1, 1, 2, 4, 3, 9. So those are the points that don't have any negatives. And then because it's a palindrome, all of these points can be reflected to the other side in a symmetric way, so like this. And then that's 7 points plotted, but if we plotted 7 million points, or connect the dots or whatever, the following kind of picture emerges. So we've seen that picture before. This shape is called a parabola. You can see that a parabola is symmetric. You can see it in the picture, and you can see it on the table because it's a palindrome. Now, it's hard to tell because I drew that big dot right there. But if you could zoom in, you would see that parabola is smooth. So it's the same kind of like if you looked at a satellite dish, like a DirecTV dish or whatever, satellite dish. If you ever looked at one, they don't like have a corner in the bottom. They're smooth. This one is also smooth. A satellite dish is a two-dimensional parabola. All right. But nevertheless, it's not pointy. It's not a corner like absolute value, but it does have. It's kind of V-ish, like an absolute value, and as a result, the behavior is going to be quite similar where equations are concerned. So. We could say concerning equations. If we want to solve x squared is c, then same trick that we've used so many times. Y is x squared. Y is c. This is going to be a horizontal line, this a parabola, and there's 3 possibilities. C could be negative, C could be 0, C could be positive. So just like the absolute value case, no intersections, 1 intersection, 2 intersections. Because, you know, I drew that just barely above because otherwise you wouldn't be able to see it. But there's just 1 intersection right at the bottom. So a typical example of this kind would be something like, x squared is, say, -5. So what could we square? What real number could we square so that we would get 5? -5, I mean to say. Nothing, right? Because if we squared a negative number, the result will be positive. And so it couldn't be -5. If we squared a positive number, the result would be 5. And if we squared 0, the result would be 0. No intersections, no solution. This one, x squared is 0. So what squares to become 0? Just 0. How many different things can square to become 0? Just 1. Okay, so x squared is 5. So, are there going to be any solutions? How many? Two. Two different ones. What squares to 5? Square root of 5, right? That's its name, right? What squares to 7? Square root of 7. What squares to potato? Square root of potato, whatever that is, right? Yeah, no solution. Okay. So, there's two possibilities. Is that on the one hand, x could be the square root of 5. On the other hand, x could be negative square root of 5. So generally, up here, that number is the square root of c, and this number is negative square root of c. All right. So let's let's see just a little bit more about that. The reason why it works this way, and another, absolute value is v-ish, and squaring is v-ish, and here's a way that they are connected. So we have the definition of square root, right? We have the definition of square root. We learned it a long time ago. We said that, essentially that if you want to get a square to move to the other side, then when you move a square to the other side, it becomes a square root. You move a cube to the other side, a cube root, etc. All right? So, I could say recall something simple. Something like if we had the equation 3x is c, something very simple. If we wanted to get x by itself, that is to say, if we wanted this multiplied by 3 to move to the other side, then over here it's multiplied by 3, but when it moves over there, it's what? Well, divide by 3. So over here, multiply by 3, over here, divide by 3. All right? So here, what we want is we've got x squared is c. And what we want, in some sense, is we want the square to change sides. So when the square moves to the other side, what does it become? Square root. So this is square root of c. And what's this? It's not x. So the most common wrong answer is to say that this is x. So now, let's be clear about why this can't be x. Why it can't be x. What do you think?
Because since we had a square root, it has to be either x or negative x.
Right.
So the absolute value of x.
Right. So having a look at the picture, you can see that how many solutions should there be? There should be 2. As written, currently, there's just 1. So what's happening is that a line, because there's just one intersection, that 3 can just move to the other side and never look back, right? And not leave anything behind. But now, because of that, because there's 2 intersections, that square root can't really just entirely switch sides and never look back. Rather, it leaves something behind. It leaves this behind, the absolute value. And alternatively, if you like to see, you can put another step in there in the following way. You can say, well, I'll take x squared is c, and then I'll compute the square root of both sides. And then remember from when we talked about absolute value and square root initially, we very carefully considered what is the square root of x squared? Well, it's absolute value of x. So however you like to think about it. So an example of solving this kind of stuff. So 3 columns, 1, 2, 3. So here's a typical example. So please solve. Something like x minus 7 square that is equal to negative 8. So what I want you to observe is that structurally this equation is like this kind we're talking about. So if I take this and just cover it up, then you can see I'm asking in some sense, well, what can I square to get negative 8? Well, what? Nothing. There's nothing you can square to get negative 8. So what's the correct response to the question? There's no solution. All right. Okay. And I always like to throw these in because sometimes students get a little, seems to me, a little nervous when seeing something like this. But it's really no different than if we were to walk out to the vending machine and say, what button do I need to press so that I can have a, you know, a new car, yeah, to get a new car. Yeah, whatever, you know, whatever you like. You know, fajitas. Well, they're not in there. All right, so then x minus 7 square that equal to 0. So will this have any solutions? Yeah, right? Because now we're asking, again, if you just cover up the input to the square, you're just asking, well, what could I square so that I get 0? Just 0, right? That's it. So that means that whatever's being squared, the thing that's in there, must be 0. So x minus 7 is 0, so x is 7. All right. Then I could say, well, okay, how about x minus 7 square that equal to 8? Okay. Well, remember we're sort of going through the possibilities. So, you know, is there anything that squares to become 8? Yeah. Square root of 8. Whatever that is. So, in fact, how many solutions do we expect? 2. So algebraically, the first step is to say that, the square can move to the other side, so that this will be square root of 8. But it can't, whoa, oops, darn. I put my hand on that button. I'm just going to turn it off and on. You can do it, camera. All right, we're back. So the square moved to the other side, but it can't in some sense entirely move over. So what is left over here? Absolute value of x minus 7. So, you know, what happens is the square that square becomes absolute value. All right, so then now we're asking, what could we put into the absolute value so that square root of 8 would come out? Well, two possibilities: negative square root of 8 or positive square root of 8. So x minus 7 could be negative square root of 8, or x minus 7 could be positive square root of 8. So x could be 7 minus the square root of 8, or x could be 7 plus the square root of 8. All right. Interesting. Now, to bring this to the crunch point, the critical point, is how about the following example? So something relatively straightforward, like something like, please solve x squared minus 14x, and then how about plus 45 equals 0. So now, here's an equation that we could solve before we started talking about plotting and all that. The reason why is because we've got a quadratic equal to 0, and that particular quadratic is the nicest possible kind of quadratic. It's monic, and it factors over the integers. So how does it factor? Nine and 5. So this would be x minus 5 multiplied by x minus 9 is 0. All right. So now we've got the product of two things is 0. So this multiplied by that is 0. So either first thing is 0 or second thing is 0. So that equation splits. So x minus 5 is 0 or x minus 9 is 0. So x is 5 or x is 9. Easy enough. Now here is a very similar, seemingly similar question. So solve x squared minus 14x plus 44 is 0. So it looks really pretty similar. The only difference is that I changed that 45 to a 44. However, the stuff that we know is not going to work. You know, because you can't, specifically what's not going to work is that you're not going to be able to think of two integers whose product is 44 and whose sum is negative 14. Right? Because we could do like 1 and 44. That's not going to do it. 2 and 22. Nah. 4 and 11. Close, but that's not going to work. So none of those are going to work. So using only the information that we've covered in the class so far, you wouldn't be able to do this, using only the information we've talked about. So so we need something better, something stronger. So specifically, you know, if I could do some work which takes this equation and turns it into one like that, to where we have something squared is equal to a constant, like one of these. If I could get it into one of these three positions, then we'd be able to go, right? So, you know, what I'm saying is like, you know, this, you know, mystery something, turns it into one of these three, and then we can finish it out. Okay. So I'm going to do this the first time, and I'm just going to show you that everything that I'm doing is legal, but I'm not going to clearly explain why I'm doing everything. First, I want to show you that it can be done, and then I'm going to show you what I did on every step. So here's the idea. I see 3 terms equal to 0. So there's 3 terms, and I can see that it's a quadratic, and I can see that these 2 terms have x and that one doesn't. So I'm going to group the terms that have x. Together in a group. And I'm going to exclude that one because it doesn't have any x's, like so. All right. That's fine. You can always add parentheses. Then now in those parentheses, I'm going to work entirely in there and just basically imagine as if I can't see anything else. I'm going to add something in there. Specifically, I'm going to add the only thing that is legal to add and not change the equation. I'm going to add 0. Okay. So the way I'm going to do it, in fact, is I'm going to first add some amount and then subtract the same amount. So I could add 10 and subtract 10. Or I could add 4 and subtract 4, or I could add -5 and subtract -5. So I'm going to add some stuff in here and then subtract some stuff. So x squared minus 14x. And then, again, this is just somehow, for now, you can just think of it like magic, like a magic trick. I'm going to say, well, 49 sounds good to me. I'm going to add 49. But, I have to undo that also, so I'll say I'll also subtract 49. So add 49 and subtract 49. So now, when we started with that group, there were 2 terms in there. And now there's 4 terms, because now there's 2 new terms in there. And what I'd like for you to observe is that now the first 3 terms, they can factor in sort of a nice way. Specifically, so how do these 3 factor? Yeah. So 2 numbers whose product is 49 and whose sum is -14, -7, and -7 again. So what I'm saying is that this can be written as x minus 7, and then square that. Okay. That's curious. I'm just leaving that one there so that you can remember that I asked a question, what goes in there. So now I'm going to drop the parentheses and add the constants together. So we would get x minus 7 squared, and then -49 plus 44 is -5, so subtract 5. And now I can write x minus 7 squared is 5. Huh. Look at where we found ourselves. Right? We've got something squared is 5. Well, is there anything that will square to 5? Square root of 5 will, right? So in fact, there's 2 possibilities. So you can either jump to those directly or use absolute value as an intermediate. I'll put the absolute value just for clarity. So absolute value of x minus 7 is square root of 5. So now I'll do the split. So x minus 7 could be negative square root of 5 or square root of 5. Or x minus 7 could be the square root of 5. So, and so x is 7 minus the square root of 5, or x is 7 plus square root of 5. So, the reason why this one doesn't, this one's not easy is because, we said that there aren't integer solutions. That doesn't mean that there aren't solutions, it's just that the solutions look like this. They're not integers. So square root of 5 I know is more than 2 because 2 squared is 4. And it's got to be less than 3 because 3 squared is 9. So, this is about, I don't know, like 2.2 or something. I don't know. Interesting. So, basically what I'm saying is that from here you knew what to do. If I, on the previous page is literally a question just like that. It's this, that's really hard to see. It's this part that was new. So does anyone know the name of this this thing? It's got a weird name. This technique its name starts with C and ends with complete the square. So it's complete the square. Okay, so what is that? So what does that mean? All right. So this thing is called complete the square. So before we get to what complete the square means, I've got to remind you about the connection between in algebra and arithmetic and all that. Of course, we have kids memorize multiplication tables and things like that. So, in algebra we have this notion of product. And you can ask any grade school kid, what's 3 multiplied by 5, and they can respond. And then on the other hand, we've got geometry. And again, with grade school kids, you can draw for them a regular polygon, like a rectangle or whatever, and you can say, what's the formula for the area, or something like that, or ask them what the area is. So over here, just abstractly, we could have something like A multiplied by B. From a purely algebraic point of view. And then from a geometric point of view, we could have a rectangle. So this would be something like A that has dimensions A and B. Well, what's the area of that rectangle? A times B. So there is an intimate connection between product, which is an algebraic phenomenon, and area, which is a geometric phenomenon. And among the many things that I'd like for y'all to take away from the class, this is probably right near the top of the intimate connection between product, which is a sort of a purely algebraic phenomenon, and area, which is a geometric phenomenon. All right. So then, now we have this thing complete the square. And if your educational experience has been typical, then you've probably heard of complete the square before, and I certainly did. But I had no idea why it was called complete the square until, in fact, after I already had a PhD. It just no one ever told me, and I never considered it until I was teaching it, and then someone said, "Why is it called that?" I had to scramble. So here's the explanation. So 2 columns, one about algebra and one about geometry. So algebraically, suppose that we're dealing with sort of a simple quadratic, like x squared plus bx. Then I'm going to take that relatively simple quadratic, x squared plus bx, and I'm going to add something to it. And the only thing that I can add to it and not change it is 0. So I'm going to add 0. But just like we were doing on the previous page, the way I'm going to add zeros, I'm going to add something and then subtract the same something. I'm going to add some amount and subtract the same amount. All right. So x squared plus bx. And then now the amount that I'm going to add is going to be a fraction. It's going to be a fraction. The denominator is always going to be 2. So it's always going to be half of something. The numerator is always going to be b. So b over 2, like that. But in fact, it's not exactly b over 2 that I want. Rather, what I want is b over 2, and I want that squared. So I'm going to add that much. But the cost of adding that much is I also have to remember to subtract that much. And you can see where I did that on the previous page, because notice that I added 49 and subtracted 49, and that's negative 14. Half of that is negative 7, and negative 7 squared is 49. So can you see it? All right. So again, just like the previous page, I started with 2 terms, and now I have 4 terms. And these first 3 terms have a very nice property. They can be written as something squared. And this one will just stay. And so that can be written as something squared. So what do I need to write? So it'll look like this. Something squared. So what do I need to put in there? So so in a similar way to this, x squared. So we'll have x, yes. And then 49 means we'll have 7. So b over 2 squared means we'll have b over 2. And then this, because why is that a minus? Yeah, because that's minus. So what's this one? Plus. All right. Interesting. So this, because it's one thing squared minus another thing squared, this is called the difference of squares. All right. So that's the algebra discussion. Now the geometry discussion is that if we start with that same relatively simple quadratic, x squared plus bx, instead of taking this route, I'm going to take a different route, and I'm going to say, all right, I observed that there's 2 terms and they have a common factor of x. So I'm going to factor that out and say that this is x multiplied by x plus b. But that, because I want to sort of look at this from a geometry point of view, I'll remember that a product is related to area of a rectangle. So I'll say that this is, I'm understanding this to mean the area of this rectangle. So this will have height x and base x plus b. So that's the area of that rectangle there. And now I'm going to change the rectangle a little bit, and I want you to tell me how the area changes. So here it is initially, and what's its area now? Same, right? And what about now? Same, right? And if I was to take it and cut it into two pieces, and with just a straight line cut, then I have two pieces, and I could find the area of the one and the area of the other, and if I added them up, it'd be the same as it was initially, right? So what I'm going to do is I'm going to sort of do some surgery on this rectangle. I'm going to say, all right, first thing is I'm going to cut it right there so that that is x and this is b, meaning that I cut it right there, and now this shape right here is a square. So that's a square, x by x, and this is a rectangle, x by b. And I didn't change the area because cuts don't change the area. And now I'm going to take that that thing, and I'm going to divide it, subdivide it into two. So this is x. This is x, and if I cut this exactly in half, like that, then how wide is that piece? Yeah. So this would be b over 2, and this would be b over 2. So we've got two of those strips there, and I'm going to shade one in. Just so you can distinguish it from the other one. So again, cutting doesn't change the area, and I could take the three pieces and I could arrange them however I want. But the area of the whole thing doesn't change. So what I'm going to do is I'm going to take that shaded one and I'm going to move it. So this is x, and this is x, and this is b over 2. So now I have to show you where I'm going to put the shaded one. Well, how tall is that shaded one? X. Which means that I could take it and fit it right down there on the bottom, right? Because that is also x right there. And it would fit like this. And you know, we'd have that little corner bitten out there. So now, you know, the way things were arranged, that's a rectangle, rectangle, rectangle. But now I've got a new shape that's not a rectangle, right? Because it's got that little corner bitten out of it. But if I just cover that up for a moment, just to ignore that, then I could ask, how tall is this new shape? So just x plus b over 2, right? That's its height. X plus b over 2. And what's its width? X plus b over 2. So you're telling me that this little bit that I was covering up, if it was there, this thing would actually be a square, but it's like lacking that little corner. You might almost say that this square is incomplete, maybe, eh? Maybe. So then, you know, we could come by and say, yeah, I'm not going to abide that. I want to fix it. I want to fill it in. And then the question becomes, you know, if we want to just fill that in somehow, then, you know, how much is that? Well, notice what's missing. It's a rectangle, the little corner there that's missing. How tall is it? B over 2. And how wide is it? B over 2. So what's actually missing there is a little square. So, you know, we could fill it in. And it would be b over 2 by b over 2, But you know, it can't just come from nowhere, so we have to take it from somewhere. So I'll say that we took it from over here. And notice that this is the difference of squares. And the way that we achieved it was by adding and subtracting a little green square. Can you see it? So that's what completing the square is. Oh, we're out of time. So we'll have to, pardon me, continue this this next time. Hope you have a wonderful Monday.